So another concept bite, another topic, this time Stokes Shift. So you're all well familiar with the Stokes Shift. Here I'm using this YoPro1 molecule again and this absorption and emission. Here we have absorption on the left and fluorescence or emission on the right. Emission always happens at lower energy, longer wavelength. And it's this difference in the peak of the absorption and the peak of the emission that we're interested in this case. This difference here is called the Stokes Shift. So here I'm just adding on a potential energy diagram on the side, and I've also labelled these absorption and emission spectra with just some numbers. So these numbers, the first one means the level of the state I start in, and the second one is the level of the state I finish in. So for the biggest peak on the absorption, I start in the ground vibrational state and I excite to the excited state. I excite to the ground vibrational first electronic excited energy level. And for the shoulder, I go into the first excited vibrational energy level. We always pretty much start in the zero level. For fluorescence, I do this because of Cash's rule, but for absorption, there just isn't enough heat, there isn't enough temperature to rise a significant proportion into this first vibrational level. So for my absorption, I have these transitions. They go from the ground level to the two excited states, so the two I can see. And then for my emission, I have these two levels. Essentially, though, on this diagram, these look the same. They have the same energy gap. So why do I see this Stokes shift? Well, I have to actually think about my system in more detail. The important thing to remember is that when a molecule absorbs a photon of light or emits a photon of light, the actual transition is very fast. We're talking femtosecond kind of orders here, 10 to the minus 15 of a second. And so molecules do not get a chance to rearrange themselves. But not only do the molecules not get a chance to rearrange themselves, the solvent, the ordered solvent around them, don't get a chance to rearrange themselves either. So when we absorb light, we go from the kind of equilibrium, relaxed state of the ground state, and we excite into the first excited state, and the molecule has the structure of the ground state. But that's not the equilibrium structure of the excited state. So not only does the molecule rearrange, but so does the solvent around it. And solvent makes a huge difference here. We can see very different Stokes shifts depending on solvent environment. So fluorescence takes quite a long time, 10 to the minus 9 of a second, and there's plenty of time for the molecule and the solvent to kind of jiggle around and reorder. And by doing that, I stabilise the excited state, but I destabilise the ground state. It is both of these processes that are going on. It's not just I stabilise the excited state. So I stabilise the excited state, and eventually when I see emission, I have an instantaneous transition, and the structure that I have is the optimized structure for the excited state. And so the molecule again will reorder itself and it will go around this cycle. So that's the origin of the Stokes shift. It's this reorganization of the molecular structure, but the solvent around the molecular structure as well. Hope this helps. More to follow.